Okay, so now that the midterm is out of the way, we're going to spend the rest of today's lecture going back and doing some energy problems. I'm fully aware that there are students who probably spent the majority of last week, even if you attended the energy lectures last week, you probably spent a lot of your free time doing practice problems for the midterm. So perhaps there was not a lot of time last week for you to go back and practice some energy concepts. So let me refresh your memory a little bit. And hopefully after today's lecture, because we haven't started momentum yet, hopefully after today's lecture, this energy review will help jog your memory. And you'll have time today, at least an hour, if not more, to go back and practice some energy questions in your textbook. So without further ado, let's get started. I saw this, a physics teacher at my high school printed this out, and it was on their office door. And I saw this, I think, in grade 11. And at the time, I just said, ha ha, it's students being funny and the teacher's being a teacher, and it's a funny little comic joke. And the teacher was not there in grade 12 anymore, and they took this down. So when I took grade 12 physics, when we actually learned how to do this, my brain had actually forgotten that this comic had existed. And it wasn't until I was prepping today's lecture and trying to find some example energy questions for you guys to try that I came across it again. I'm just like, oh my God, I remember when I was like 16, 17, this question was on my physics teacher's door, and I hadn't seen it since. And I was reading through it. I'm like, this is perfect. Like it's a good starting question. It's not too difficult, and it's a great example of how students can get creative when they don't know what to do. So the question is, a 3 kilogram object is released from rest at a known height of 5 meters on a curved frictionless ramp. Again, this is where Mark Garneau was talking about when he gave a talk to the class. On Earth, we pretend a lot of the time things are frictionless, when in real life that is not the case. In space, that is absolutely true. Anyway, at the foot of the ramp, there is a spring of force constant 100 newtons. The object slides down the ramp and into the spring, compressing it an unknown distance x before it comes to rest. Find x. And the student cheekily said, no, there is an elephant in the way, and then drew a little pencil drawing of an elephant, which at the time when I was 16, 17, I absolutely died laughing. It was hilarious. Even now, honestly, as a physics teacher, it's hilarious. Every time students don't know what to do, they write little fun things on the test. It always makes us laugh. Of course, it sacrifices your grades, but if you actually have no idea what you're doing and you want to have a bit of fun, we do appreciate the jokes on our end. But I'm not saying to do that. I mean, if you write something, you might actually get some marks. But anyway. So let's use conservation of energy to figure this out. There's 2 events. There's an event before and an event after. I don't know why, but I'm not able to change my pen color. So we're just going to go with whatever it's currently set at. So before, the elephant is up here. So that's kind of before. Maybe I'll label this before. And after is when it falls down and compresses the spring. So using conservation of energy, we say the total amount of energy before an event has to be the same amount of energy after the event, right? Energy cannot be created or destroyed. So we learned up until now, this point in the course, we've only really learned about 3 types of conservative force of energies and 1 non-conservative force of energy, which would be friction. So we can set up our full-blown conservation of energy equation and cancel things as we need to. So I would say gravitational energy before plus spring energy before plus kinetic energy before is going to equal gravitational energy after plus spring energy after plus kinetic energy after. So I ask myself, before the object falls, is there gravitational potential energy? Is there MGH? Yes, there is. It has 5 meters of height, so we cannot cross that off. Springs, before anything happens, before the object falls, are there any springs that are compressed or elongated? No. So this goes to 0. Before the object is dropped, is there any motion? Is there any kinetic energy? No, it's stationary. After the object slides down the ramp, after the object compresses the spring, and then after the object comes to rest, right? That's after. Is there any height left? No. Is there any kinetic energy? Well, there used to be. the gravitational potential energy got converted to kinetic energy, and then the kinetic energy got further converted into spring energy. And then the after scenario that we're talking about is after it comes to rest, when it compresses the spring and it comes to rest. So at the after scenario 2 is no, it's not moving. So the only thing left is the spring energy. So our conservation of energy equation becomes gravitational energy gets transformed into spring energy after. So that's going to be mgh, and the spring energy is 1/2 k x squared, and we're asked to find x. So here we see that x is going to be equal to the square root of 2mgh all over k. And I mean, you've seen from the midterm that my calculator and I do not have a good relationship. In fact, I'm actually more accurate coming up with values when I don't use a calculator, right? When I use my approximation techniques, I tend to be more accurate that way. So I won't even pretend to try to calculate a value here, but there's the formula. Let's just make sure we have all the values. Do we have m? Yeah, it's 3 kilograms. G is a constant. Do we have h? Yep, it's 5 meters. Do we have k? Yep, k is 100. So we have all our values there. You can go ahead and find your x. And then part B says, does the object continue to move after it comes to rest? The answer to this is yes, because spring energy is a conservative type of energy, or I should say Hooke's law, the spring force is a conservative force, which means when you have stored energy, you can release the energy and transform it back into something else without losing it. Like friction, for instance, you lose, right? You never get that amount of energy back. But spring energy, you know, if you elongate a rubber band and let go, the rubber band will like ricochet forwards. It'll try to regain its original shape, and it'll transform the energy stored in the rubber or in the spring, and it'll transform it into kinetic energy. So after the block momentarily comes to rest, the spring will push it backwards up the ramp. And so the spring energy will turn back into kinetic, and then the kinetic will go up the ramp and then turn back into potential. And as long as it's frictionless, it'll keep doing that forever. It'll oscillate up the ramp, down the ramp, up the ramp, down the ramp forever. Anyway, so that was a good little warm-up. This was a question we had on the lecture slides that we did not have time to get to. So I figured now would be a kind of a good time to go back and do this. It's actually sort of applicable to your conservation of energy lab as well. So that's kind of another reason why I thought it would be a good idea to kind of go back as a class and do this. So let me just make this a little bit smaller so we've got some room to write. So the question says, we have a spring with a known spring constant, physicists and words. So I'm just going to write this down to tell my brain that we have it. So a spring is fixed at the top of a frictionless plane, beautiful, no friction, inclined at 40 degrees, a 1 kilogram box is launched upward from an initial position that is 0.6 meters from the end of the relaxed spring. So D1 equals 0.6 meters. For those of you, you know, whose brain is sort of in the conservation of energy lab, this is very similar to the distance values that we gave you of the object. We have what is it called? Oh, I'm drawing a blank right now. It's like a position meter. It sends out infrared pulses. It's the blue thing. It's the blue object in the lab video. And it measures position. It measures how far away an object is from that blue position sensor. So a distance of 0.6 meters would be like the blue position sensor here measuring that the cart is 0.6 meters down the ramp. And as you launch the cart up the ramp, that distance shrinks, right? The value will get smaller because the cart is becoming closer and closer and closer to the sensor. So that's how you can kind of interpret those values. And that's kind of why this question is relevant to the conservation of energy lab that you're going to do. Okay, keep reading. The relaxed spring, okay, it's launched up with an initial kinetic energy of 16 joules. Okay, what is the kinetic energy of the block at the instant it has compressed the spring 0.2 meters? All right, so we want to know the kinetic energy final when the spring energy final is 1/2 K 0.2 squared. So they're asking for energy, so that tells me that we have to approach this using conservation of energy. So let's just go ahead and set that up. I know ahead of time that we're going to need, oh, I can't put more space because it will not. Okay, well, we're going to have to try our best. Can I move this down? Maybe. No, I can't. Well, I'll move it down later if I need to. I'll figure it out. So total energy before equals total energy after. Before anything happens, the object is down here. And so let's just write out EK plus E spring plus EG equals EK prime plus EG prime plus E spring prime. I guess plus work done, but it says there's no friction, so there's no work done by a non-conservative force. So initially, we ask ourselves, is there kinetic energy? Yes, there is. It says that it was launched up from the bottom, so we know it has an initial speed. Is the spring compressed at the bottom? No. Does there exist any height? Yes and no. I mean, the presence of an altitude is subject to your frame of reference. You know, where do you want to choose the ground, right? We are told that it is a distance of 0.6 meters away from the top of the spring, or I guess bottom of the spring, I should say. So we can take this to be a height of 0 if we wanted it to be. And then we can take this to be a height of non-zero, and we can measure the difference, delta H, right? It's mg delta H. We don't care how high off the tabletop it is. We care what the change in height is, mg delta H. So we can say the final position is up here, and the starting position is down here. All we have to do is measure that delta H, and we can do that. So I'm going to assume that there is no gravitational potential energy at the start, because I'm going to assume wherever the block starts, that's going to be a 0 gravitational potential energy. Afterwards, is there gravitational potential energy? Yes, because it got elevated. Is there spring energy? Yes, because the spring got compressed. The question tells you that right there, spring got compressed. And is there kinetic energy? Presumably yes, because it's asking you for the kinetic energy after the spring is compressed. So we actually can't really simplify anything on the right-hand side. So that gives us our values. We have EK equals EK prime plus mg delta H plus 1/2 K x squared. Now, why didn't I say EK prime was 1/2 mv squared? It's because they didn't ask us for speed. The question specifically asked us for what is the kinetic energy of the block. They're asking us for EK prime in joules, not speed or anything like that. So I'm just going to keep it as EK prime. Okay, so let's continue to plug in some of our values here. EK prime is what we're looking for. So EK prime is going to be EK minus mg delta H minus 1/2 K x squared. And here's where things get a little bit fun. The change in height. Well, the change in height, and I still cannot change, nope, cannot change my color. So the change in height is going to be measured by this triangle here, and we know theta. So that's going to be the opposite over hypotenuse, so sine theta. So mg delta H is actually going to be d sine theta. We know this from the geometry, d sine theta, and minus 1/2 K x squared. We have x. It was stated in the question to be 20 centimeters or 0.2 meters. So there is our equation, and right there. And everything in here is stated in the problem. You know, EK, we have, it was what, 16, I believe it was 16 joules. Yep, 16 joules. Mass we're given, 1 kilogram. Distance is 0.6. Theta is 40. K is what, 200, and X is 0.2. So we have everything in the problem. So you can just go ahead and calculate that value if you'd like. Again, I'm not good with calculators, so I'm not even going to go there. You know, I could just type it into Google and have Google crunch the numbers if I care to. Part B, with what kinetic energy must the block be projected up the ramp? So what kinetic energy initially for it to momentarily stop when it has compressed the spring a distance of 0.4 meters, which means that's when the spring energy is going to be 1/2 K 0.4 squared. Okay, so now we're working backwards. We set up our conservation of energy equation again. Energy total equals energy total prime. And beforehand, we're having some sort of initial kinetic energy, as we did before. Now, the difference is we're not told that it's 16 joules. We're asked to solve what it would need to be in order to reach a certain point on up the ramp. So afterwards, we want it to compress the spring by this much and stops momentarily. So that keyword there of stops momentarily after it compresses the string this much tells me that the kinetic energy after is equal to 0. It's kind of like when you throw a ball up in the air, momentarily it comes to rest at the apex of the trajectory, momentarily. So that's what's going to happen here. However, there is a spring energy after, and there is absolutely a gravitational energy after. So we go through, and we see here, this is going to be 1/2 K x squared plus mg and delta d. Now here's the thing. Oh, hold on. Hold on. We got to go back, and there's something to do with that previous one there. You'll see momentarily. Mg delta h. Let me write delta h here equals ek initial. Let me draw you that hypotenuse again. So we have the object starting here. We know this distance is 0.6. But it compresses the spring by how much? 0.4. So we used the wrong d value last time. So I'll correct for it this time, and I'll go back and I'll fix the equation last time. So my delta h value is this, delta h. But my hypotenuse is not delta d, or sorry, my hypotenuse is not d, it's actually d plus x. So this is going to be 1/2 K, what was x? I'll just say x, plus mg, and my hypotenuse is d plus x sine theta. And what do they want? Do they want the initial speed? Got to go back and see. Nope, with what kinetic energy? Okay, so they're asking for kinetic energy. If they ask for speed, you could easily calculate speed. You can just, if you wanted to, you could say this equals 1/2 mv squared, and you could just solve for speed. Anyway, back to here, we kind of, or I overlooked that the hypotenuse is not d. The hypotenuse is in fact d, oops, too close to the bottom of the screen. The hypotenuse is in fact d plus, what's the compression of the spring? 0.2? D plus x sine theta. There you go. Okay, so there is your final equation for part B as well. Okay, so conservation of energy, you've seen now, we did a few example questions last Wednesday. We've done sort of 2, maybe 3 if you include part A and B separately here. 3 different questions for conservation of energy. You see that it's always the same start. E total equals E total prime, and then I write out the full conservation of energy equation. I still can't change my color. We write out the full conservation of energy equation. EK plus E spring plus EG equals EK prime plus EG prime plus E spring prime plus work. I always write that out, and I always ask myself, for our specific situation, do I have a spring beforehand? No, okay, it goes to 0. Do I have any elevation beforehand? Nope, so the gravitational potential energy goes to 0. And then I ask my same questions afterwards, and I can cross things out as I need to, specifically based on my current situation. So it's always the same start and end equations. Let's do, I think we've got time for maybe another one, so I'll see if I can pack another one into there. We already did a spring one, so I don't know, I found this question in a textbook somewhere. It talked about hanging a fish off of a spring. I thought that was hilarious because it's very, very indicative of kind of a physicist's brain. We're just kind of zany like that. But anyway, we've already done a spring question. So let's do a circular motion question in the last few minutes that we have here. A small block with mass, okay, mass equals 0.04 kilograms. Slides in a vertical circle. Okay, so it's a vertical circle of radius r equals 0.5 meters on the inside of a circular track. Yeah. During one of the revolutions of the block, when the block is at the bottom of its path, point A, okay, point A. The normal force of the block by the track has this magnitude. Okay, so Fn at the bottom is going to equal 3.95. In the same revolution, when the block reaches the top of its path, point B, the normal force at the top or bottom, yeah, top. I should really say point A and B because B could mean point B. So I'll say at point A, and the normal force at point B is 0.68 newtons. How much work is done on the block by friction during the motion of the block from point A to point B? So, point B is up here. So they're asking for the force due to friction. So that tells me, for the work done due to the force of friction. So that tells me we have to start with our conservation of energy equations. E total equals E total prime. So here our before and after are going to be at the bottom of the loop and the top of the loop, or point A and point B. So at point A, well, actually, let's just write out this whole thing. EG plus E spring plus E kinetic equals EG prime plus E spring prime plus E kinetic prime plus work done due to friction. Okay. So at the bottom of the loop, is there any gravitational potential energy? No, because we're at the bottom. That goes to 0. Is there any springs that are compressed or elongated at the bottom of the loop? No. Is there kinetic energy? Yes, there is. So can't eliminate that. At the top of the loop, is there gravitational potential energy? Yes, there is, because it has raised up a distance of 2r. Is there a spring at the top of the loop? No, there isn't. Is there speed at the top of the loop? Yes, there presumably is. Otherwise, it wouldn't be in circular motion. It would just fall. So there's definitely a speed. And is there friction in the problem? Yes, there is. So this gives us our equation. So 1/2 mv at point A squared equals mg, my delta h, my change in height. My change in height between the bottom and the top is 2 times the radius, plus 1/2 mv at point B squared, plus the work done due to friction. All right, do we have the speed at the bottom of the loop? No. Do we have the speed at the top of the loop? No. So this tells me we need to pull in something else. So what else do they give us? Well, they give us normal force at the top and the bottom. So maybe we can use what we learned previously, because normal force, they give you a force. Maybe we just kind of draw a free body diagram, do F net equals ma, see what falls out. If you recall, my general advice to students was, as soon as you have to deal with forces, start with a free body diagram, do F net equals ma. So let's do that, see what happens. So free body diagram at point A. Point A is the bottom of the loop. So we've got force of gravity down, we have normal force up, and this gives us a net force of normal force minus gravity equals mv squared over r. Oh, there's my v squared, mv squared over r. That's how you can get your v squared. They give you normal force, and we have gravity, so we can find v squared easily enough. So this is going to be r times Fn at point A minus mg. Nope, sorry. Yeah, minus mg is equal to mv squared. There you go. Sorry, at point A, I should say. So I can take this value and I can plug it into this. So 1/2 mva squared. Well, what was mva squared? mva squared was r times Fna minus mg. Okay, so this is going to be r times Fna minus mg equals mg times 2r plus, oh boy, 1/2 m v b, so v at the top, okay? So let's do another free body diagram at point B. We have gravity down, we have normal force down. That means our net force is Fg plus the normal force equals mv squared over r. V at B, I should say. So r times mg plus Fn at point B is going to equal to mvb squared. So here I see m. Oh, okay, I can actually replace this m as well. Nice. So this is going to be r, put the bracket in the wrong spot, r times mg minus fnb plus work done due to friction. All right. So let's see what we have. Do we have radius? Oh, I'm using big R and capital R. I guess that's my mistake. I'll use capital R, then I'll be consistent. Okay, do we have radius? Yes, we do, 0.5. Do we have FNA? Yes, it is, oh, I forgot the newtons there, 3.95 newtons. Mass, 0.04. Yes, G is a constant. Equals M, yes, G, yes, R, yes, R, yes, M, yes, G, yes, Fn, B, yes. So work that, yeah, so there, this is the only thing we need. So you can rearrange for work F, and that'll answer how much work is done by friction if you solve for W sub F. So we're running a little bit over time, so I don't want to waste time rearranging. I have enough faith that students can rearrange equations. It's just simple algebra. So I'll let you rearrange the equation, but all of the quantities in there are given. So you can just plug everything in and solve for the work done due to friction. Okay, so I hope this practice on energy was helpful. We reviewed the notion of conservative versus a non-conservative force, how springs were conservative, kinetic energy can be transformed and returned, that's conservative, gravitational energy is conserved. But friction is non-conservative, meaning if you lose some energy due to friction, you account for it mathematically, right? It pops up as work done due to friction. But once you've used up that heat, it dissipates into the air, and that heat gets transformed into other things later on, but it's out of your system. So that would be a non-conservative force. So we reviewed that. We reviewed the notion of conservation of energy and kind of how to apply it. And we saw it applied in a few different scenarios with ramps, with springs, with loops, and with friction. So hopefully this was enough of a review from last week's material to jog your memory. And after today's lecture, you can go back and you can spend at least an hour, hopefully more, practicing some conservation of energy questions. And hopefully with enough practice, you realize that all the energy questions at the end of the day are honestly the same question. You've seen me now do four or five questions today on energy, and they all start with the same thing. Some sort of picture, E total equals E total prime, and then writing out the full-blown conservation of energy equation. And just asking yourself every single time, do I have a spring? No, cross it out. Do I have gravitational energy? No, cross it out. And every scenario is going to be different. And so you're going to have a different combination of things you cross out and keep. And that is what makes that analysis tailored to that situation. But the approach is the same. The last question we did here, I showed you how one of the quantities may not be explicitly given in the question, but you might need to borrow ideas from previous chapters, like dynamics, free body diagrams, Newton's second law, to sort of solve for an equation and plug the equation in to eliminate a variable that way. So energy is not a standalone chapter, right? It definitely relates to other chapters as well. So I encourage you all, please go home and do some practice. Okay, I think that's all for the material today. I'm going to stop the recording, and then I'm going to check the chat for some questions on what we've done. If you're watching on YouTube, I will see you tomorrow.